Welcome to the Explainer. We love to take really complex topics and make them super easy to understand. And today we are diving deep into the anatomy of an expert system. This is going to be your ultimate guide to absolutely ace that upcoming exam. Okay, so let's just start with the biggest question of all, right? The one that expert systems were actually built to solve. How in the world you digitize a human expert's mind? I mean, think about it. We're talking about decades of experience, all that intuition, those gut feelings, those little rules of thumb. How do you bottle all of that up and put it into a computer program that can think and solve problems just like a real pro? All right, so here it is. This is the definition you absolutely have to burn into your brain for the exam. At its core, an expert system is a computer program that uses human knowledge to solve problems that, well, normally need a human expert. And look closely. There are two magic ingredients here. Facts, that's the stuff you'd find in a textbook, and heuristics. Heuristics are the real game changer. They're those rules of thumb, the educated guesses an expert makes from experience. That right there is the secret sauce. So here's what we've got on tap today. First, we'll cover what an expert system actually is. Then we'll break down the 6 core components. After that, we'll see how the system thinks. We'll look at some real-world examples, and then we'll wrap it all up with a final exam review to make sure you're good to go. Okay, first up, what is an expert system? Let's get right into it. Now, before we start pulling it apart piece by piece, you got to understand the fundamental difference between these systems and, the regular old software you use every day. And this right here is a huge deal. On one side, you've got expert systems, and on the other, your conventional systems. Now, the number one thing to remember for your exam, seriously, star this, is that in an expert system, the knowledge, what it knows, is totally separate from the control or how it thinks. In regular programs, that stuff is all tangled together. This separation makes expert systems way easier to update. And get this, because they use those heuristic rules of thumb, they can actually work with missing information. And yep, they can even make mistakes, just like a person. And maybe the coolest part, they can explain how they got an answer. You can't ask Microsoft Word why it did something, right? All right, now for the main event. Let's talk about those 6 core components. We are literally going to dissect the architecture of an expert system. Think of it like an anatomy class, but for a piece of code. First on our list is the knowledge base. This is the intelligence source, the system's specialized library. But don't just picture a dusty old database of facts. No way. It's packed with 2 kinds of knowledge. Declarative knowledge, which are the raw facts, and procedural knowledge, and this is the good stuff. The heuristics, those critical if this, then that rules that an expert uses every single day. Okay, so if the knowledge base is the library, then the inference engine is the brain of the whole operation. This is the part that does the actual thinking. It grabs a problem, goes to the knowledge base, pulls out the right facts and rules, and then uses them to reason its way to an answer. It's the engine that drives everything. Next up, the user interface. This is pretty straightforward. It's how you and I talk to the system. It's the language processor that makes communication friendly and problem-oriented. The goal here is to let someone who isn't a tech genius interact with it. Ask questions in plain English and get answers they can actually understand. And then we have the blackboard, or the workplace. The best way to think about this is like a detective's corkboard or a scientist's scratchpad. It's a working memory area where the system jots down the current problem, keeps track of clues and intermediate results, and pins up any new hypotheses that pop up along the way. Now, this next one, the explanation subsystem or justifier, is absolutely crucial. It's what builds trust. It lets the system show its work. So you can literally ask it, hey, how did you come up with that? Or why are you asking me for this specific piece of information? And it will lay out the exact chain of reasoning it followed. That kind of transparency is a total game changer. And last but not least, number 6, the knowledge acquisition subsystem. So how does all this brilliant expertise get from a human's head into the computer? Well, this is how. It's a set of tools that a person called a knowledge engineer uses to basically interview human specialists, pull out their knowledge, and translate it into the facts and rules the knowledge base can understand. Okay, so we've seen all the parts. Now, let's see how the system actually thinks. We're going to pop the hood and take a look inside that inference engine. How does this thing actually piece everything together to come up with an answer? The whole process boils down to this really simple but powerful loop called the recognize act cycle. It's just 3 steps, over and over. First, recognize. The engine looks at all the current facts on the blackboard and sees which if rules match. Second, conflict resolution. If a bunch of rules match, it has to pick just one. And third, act. It fires that rules then part, which usually adds a brand new fact to the blackboard. And then the whole cycle starts again. Lather, rinse, repeat. So what about that conflict resolution step? What happens when, say, 5 different rules all match the facts at the same time? Which one does it pick? Well, the inference engine has its own little management team for this. The scheduler is like the manager who looks at the options and prioritizes which rule is most important to fire next. The interpreter is the worker who actually executes the chosen rule. And the consistency enforcer is like quality control, making sure that whatever new fact gets added doesn't contradict anything the system already knows. Okay, but let's be real. The world isn't black and white, right? Facts are often, well, fuzzy. In a field like medicine, a symptom doesn't prove a disease. It just suggests it. So how does a system deal with all that gray area? That's where something called certainty factors, or CF, come into play. It's a way for the system to reason with imprecise knowledge. It's actually a pretty cool system. Instead of just true or false, it uses a scale from -1 to +1. +1 means something is absolutely 100% true. -1 means it's definitely false. And 0 means I have no idea, there's no evidence either way. Everything in between lets the system express degrees of belief or disbelief, so it can weigh all the evidence, even conflicting stuff, and come to a conclusion that isn't just a yes or no, but a probably with a specific level of confidence. All right, so we've got the theory down, we've looked at all the parts, now let's see these things in action. How does this architecture actually look when it's out in the real world, doing its job in a hospital or a bank? This is where it all comes together beautifully. Let's take a medical diagnosis system like the famous one called MySyn. The knowledge base? That's basically a massive library of medical textbooks and diagnostic rules. The inference engine? Think of it as the senior doctor, using all that knowledge to reason through a case. The blackboard is the patient's chart, where all the current symptoms and test results are kept. And the user interface is the conversation it has with a junior doctor, asking questions and providing a diagnosis. And it's the exact same idea in a totally different field, like financial compliance. How do you build a system to catch criminals laundering money? Well, you use that knowledge acquisition subsystem we talked about. Knowledge engineers sit down with anti-money laundering experts and pull out all their secrets, how they spot tricky techniques like smurfing or layering. They then turn that human expertise into rules the system can use to flag suspicious activity. Okay, deep breath. We've gone through a ton of information. So now it's time for your final exam review. Let's lock in the absolute key takeaways you need to know. All right, first things first. Number 1, separation is key. The knowledge base, what it knows, is separate from the inference engine, how it thinks. That is the single most important characteristic. Number 2, heuristics rule. These systems use rules of thumb, which is awesome because they can solve problems even with missing info, but it also means they can make mistakes. And 3, explanation matters. A good expert system can always tell you how it got an answer and why it's asking a question. And don't forget the other big concepts. Remember the 2 ways of thinking. Backward chaining is goal-driven. It's like a detective. It starts with a possible answer, like, does this patient have meningitis? And works backward to find clues. Perfect for diagnosis. Then there's forward chaining, which is data-driven. It starts with the facts you have, like, the soil is low on nitrogen, and works forward to see where that leads. Great for things like planning. And finally, when the facts get fuzzy, certainty factors are how the system handles all that uncertainty. So, to wrap this all up, let me leave you with a thought. Now that you know how to build one of these things, at least in theory, think about it. If you could build an expert system for any field out there, what problem would you solve? What incredible human expertise is so valuable that it's worth capturing and sharing with the world?